it's some overview of one of the basic questions in my research area. So hopefully I will convince you that it is both interesting and non-trivial. And also there is no test, but I will have to say I do not know the name of the 7 dwarfs that are on the screen. So congratulations if you do. Okay, so it's testing if your data is uniformly distributed. What exactly does that mean? And you know, there's going to be a lot of theory, but also I'm going to try to convince you that this has some practical applications. So it's some question that seems very basic from a statistical point of view. You've got n IID samples. So IID is independent and identically distributed from some unknown probability distribution over k elements. So here I'm going to use k as like the domain size. Think of that as being very, very large. And you have one question. You want to know, well, is that unknown distribution the uniform distribution that puts equal probability on all of those k elements? Or like, alternatively, is it statistically far from being the uniform distribution? And we have to define what it means to be statistically far. So one of the notions that is widely considered is total variation distance. So is it at total variation distance at least epsilon from the uniform distribution? And I forgot to say, if you have any questions, please ask in the chat or like unmute yourself and ask. Even if it's just a question about like, can you repeat what you just said? I know that sometimes my accent is a bit hard to understand. So here's the question. I've got n observations from some unknown probability distribution over k elements, and I want to know whether that distribution is uniform or far from uniform. And just as a little test, not quite a test, just here are a few of the things you could see. So I just took some, I had like some made up distributions. Some of them are uniform, some of them are not. Domain size k is equal to 50, and I take n, a different number of samples, and I plot like the frequency according to which I see each element. So the empirical distribution. What can you say? Which ones are uniform, which ones are not? So some of them, it's pretty clear it's probably not from the uniform distribution. Like the one on the top left definitely doesn't look like it. The one on the top right, probably. I mean, I took a lot of samples, right? It was like 1 million or 10 million, and like it looks pretty uniform. So like, yeah, maybe. And the two at the bottom, it's actually not that clear, right? Because sure, that doesn't look very uniform, but at the same time, I didn't take that many samples from the distribution. I don't have that many observations. So I do expect some variations from a uniform. So the point of this is just saying like the obvious thing, just take a bunch of samples and look at the empirical distribution. Does not necessarily work, at least it's not trivial. And if you remember what I just said, k, the domain size, is supposed to be very, very large, right? So my goal as a computer scientist is to do something that requires the least effort possible. So I want to take very few observations before being able to conclude. I want to have as few data points as possible before I can be confident saying like, yes, this is uniform, or no, it's not uniform. So in particular, I would like n to be much smaller than k, ideally, or like at least, you know, small. And if you do that, well, you're not going to see every domain element. Just if you take fewer samples than the domain size, the chances that you actually see each domain element even once are like 0. So the point of this slide is to convince you that it's not actually an obvious question. It's not obvious what the right thing to do is, especially since we're in that finite sample regime where we want to take very few samples. We don't assume that n goes to infinity and things are nice and asymptotic. So I just said we're going to look at that problem where it's either uniform or we want to detect whether it's uniform or far from uniform in total variation distance. Just here's the definition of total variation distance. If you've never seen it, well, it is what it is. There are two interpretations of that. The one in the middle is saying that this is the maximum discrepancy put on any subset of the domain by two distributions, which is equivalent to saying like what is the best advantage I could have given one observation to distinguish between the two distributions. The other one, which is kind of nice, is saying it's actually exactly half the L1 distance between the distributions if I see them as like k-dimensional vectors of numbers. So both are equivalent, but sometimes one of them is nicer than the other. The first one has a nicer interpretation in terms of distinguishability. The second one has a nicer interpretation in terms of, well, linear algebra, inequalities, and making proofs work. So that's total variation distance. And this is what I want. I want a uniformity testing algorithm. It's an algorithm that takes as input a value epsilon, either I'm uniform or like at distance, at least epsilon from uniform. And it also takes n IID samples from some unknown distribution, P. Let's call it P, over a domain of size K. And that algorithm has two options. It says accept or reject. And the guarantee I want is if my distribution was actually uniform, it needs to accept with high probability. Let's say probability at least 99%. But if my distribution was far from uniform, it has to reject, similarly with high probability, at least 99%. So at that point, I don't know if there are some people like that are familiar with other jargon, but like basically like here I set the type 1 and type 2 errors both to be 1%. And my null hypothesis is it's uniform, and my alternative is the composite hypothesis far from uniform. Is there any question about this formulation? I'm not sure exactly where to look at, so. Okay. So there might be some questions. One of them is, for example, what's so special about uniformity? I mean, yeah, sure, this is nice. The uniform distribution on the domain is nice and simple to describe, but maybe I want to test something else. Maybe I have a model in mind and I want to say like, oh, is the data coming from the model I have in mind? Think of that as like maybe a binomial distribution or like some weird but explicitly known distribution that comes from like some expert knowledge or like some experiment you've run. The point is uniformity testing is basically equivalent. If I can do uniformity testing, I can do any test to a known distribution that's called identity testing. So I can replace uniform by any distribution that you know and that you choose. There is a formal reduction in the computer science sense. So like I can use an algorithm for uniformity testing for like the margin error case. And conversely, if I know how to do the margin error case, well, I know how to do uniformity testing. So uniformity testing is basically without loss of generality. And so I will just focus on uniformity. The second one is 99% is weird, a bit arbitrary. Why do I want probability of success 99% and not, well, 51% or like 99.99% or like even more, 1 minus delta for some delta of my choosing. And what I want to say is like 99% is arbitrary, but you can always boost the probability of success to like 1 minus delta by paying a little bit more. So it's not the optimal thing to do, but let's say that's enough. So if you take a multiplicative log 1 over delta times as much data, you can replace that 0.99 by like 1 minus delta for any delta as small as you want. And the idea is very simple. You take much more data, you divide that into chunks, you run your algorithm independently on all those chunks of data, and then you take the majority vote. That's called the median trick, or it has other names. And the idea is like if each chunk is correct with probability 99%, well, the probability that more than half of the chunk of the different runs of the algorithms are going to be incorrect decreases exponentially fast. So 0.99% is arbitrary. Let's just focus on this. It makes things a bit nicer. And finally, well, here's the problem. I want to find the minimum n, like the minimum data size for which I can solve this problem. And this is known. It took a while, but we know the right dependence with respect to all the parameters. I think even like some work has been working on the constant in the big theta there. Basically, what you need is square root of the domain size divided by epsilon square, many data points. Now, I don't know how many of you find that square root case surprising or not. Raise your hand if you find that surprising, or if you had expected something else, maybe. Or the idea here is, you can think of that as the birthday paradox. before I take at least square root k samples, I will not, even for the uniform distribution, I will not see the same element twice. But then if I don't see the same element twice, I just see a bunch of elements exactly once, there is not much I can say at all about it. In particular, I can't decide whether it's uniform on the whole domain or uniform on half of the domain. And I have no information to conclude. So I need at least square root k. And turns out once you get square root k, you can actually do something like that. We'll see, and that allows you to detect whether it's uniform or not. So the right thing we're going to try to see in various ways is I need to take square root k over epsilon square data points before I can conclude with pretty high confidence, yes, this is the underlying distribution is uniform, or no, the underlying distribution is definitely not uniform. It's a distance at least epsilon from it. Again, if there is any question, please feel free to interrupt at any point. So, any idea about how one could get that square root k over epsilon square? Again, I don't expect necessarily that. It's more of a segue, but another thing is not just how, it's also what we care about. So it's really nice to have a bound on n, saying like I achieve the minimum data size I need to be able to solve the problem. That's data efficiency. I'm going to call that the sample complexity of the algorithm, and that's my main focus usually. But there are many other things you want to do. Time efficiency. Maybe you actually care about a fast algorithm. Or memory efficiency. How much memory does my algorithm require? It should not be too much, hopefully. In particular, if you want to implement that on small devices or like sensors or in a streaming fashion, etc. There's also simplicity. I mean, if you've taken some algorithms class, you probably have seen some algorithms that look like monsters. It's a sequence of reductions and like nobody understands exactly what they're supposed to do. It's nice to have an algorithm that is simple to describe, because simple to describe also probably means simple to implement, and also fewer occasions to mess up the implementation or to have moving parts that will go wrong. As a theoretician, there's also the other side of simplicity. Is the algorithm simple to analyze? Nobody likes a 7-page proof. So if the algorithm is actually simple to analyze and easy to see why it works, that's really nice. There's a point, another one, that is robustness. So if you remember the definition of the problem I'm trying to solve here, either the distribution is exactly uniform or it's far from uniform. But I mean, in real life, things are very not nice. It's not going to be exactly uniform. It's going to be roughly uniform. So that's the robustness part. The algorithms, all of them will have some built-in kind of tolerance to model misspecification. Even if it's not exactly uniform, it's still going to accept. But how much of that do you have? Is it like, oh, but if you're like really, really close, you're going to accept? Or if you're even like moderately close to uniform, the algorithm is still going to be, yeah, it's fine. You're close enough to uniform for me. So that's tolerance or robustness. There's also the elegance of the algorithm. That's more like an algorithm design thing. Sometimes you just see an algorithm, it's like, no, this is ugly. Maybe it works, but this is not the right thing to do. This can't be. So it's nice to have an algorithm that also looks like, yeah, that's nice, that's elegant, but that's very subjective. And the last one is generalizable. So all that, if I want to convince you there are applications for that, these algorithms are used not as an end, right? You use them to do model selection, to figure out some property of your data before doing something else with it, or selecting the right algorithm for the task you're looking at afterwards, or like as some building block in a more general, like a bigger pipeline. A lot of times you want something more than just the guarantee. So you might want some bonus features of the algorithm. Is the algorithm also like providing like some nice robustness to outliers, some nice other things? Some of them will do, some of them won't, but it's important to keep those in mind because they might actually be critical for your application. So the point of this slide is basically to convince you that even for such a simple problem, there are multiple dimensions that are even hard to define, but you really want to keep those in mind. And that's why essentially I'm saying 7 algorithms for the same task and not like, we have one, why do we bother? Yeah, there is a question about the square root of k. Yes, so why do we expect square root of k instead of something else? So one baseline is if I wanted to learn the distribution, I would need a dependence that's k, like forget about epsilon, just like linear in the domain size. And once I've learned the distribution, I can do whatever I want, in particular check whether it's uniform or far from it. Square root k is much better, and we can achieve that if all we want to do is test whether it's uniform. And why do we need square root k is just think of the uniform distribution. I will ask you just a simpler task, distinguish between the uniform distribution and some distribution that is uniform on exactly k over 2 elements, you don't know which ones. By the birthday paradox, you will need square root k up to some constant times square root k IID samples before saying twice the same value. But if you don't see twice the same value, you can't distinguish between those two cases because all you see is a bunch of data points, each value taken exactly once. So you have no idea if it's actually uniform on the whole domain or uniform on a randomly chosen subset of k over 2 elements. So you need at least square root k to be able to say anything. Now, on the other side, where is square root k enough? We're going to see, but one rule of thumb is like, well, once you start having square root k, you will see those collisions. There will be some values that are taken at least twice. And counting those collisions is enough to distinguish between uniform or not. We're going to see exactly why. But that's roughly the idea between that square root k. Before square root k, you don't have enough information even to solve a simpler version of the problem by the birthday paradox. And after that, after square root k, you're going to have a sufficient statistic that you can compute. Hopefully that answers at this point, and some of that should become a bit clearer with the rest of the talk. So here are the 7 algorithms. I gave them names. One of them is collision-based. That's roughly the one I very briefly alluded to, and we're gonna go through that. It's the one that counts those collisions, the number of times the number of pairs of samples that take the same value. And it's called a collision because I have 2 samples and they take the same value, so they collide on some value. And it achieves the right optimal thing, square root k over epsilon square. But the analysis is a bit tricky. Then there's another one that is kind of dual to this one, is unique elements. We're going to also see what it does, but basically it counts the number of elements we see only once. So it's exactly the dual to the counting the number of elements we see twice. It also achieves the optimal sample complexity, the optimal n, but it has some restriction. The distance cannot be too small in the way we frame the problem. And there's also a reason for that you're going to see, but this is a limitation of the algorithm. Then there's something that, again, we're going to see all of those in more detail. Modify chi-square, so statisticians among you, that might ring a bell, at least the chi-square part, maybe not the modified. It achieves the optimal sample complexity. There is basically no downside to it, and it works. Then there's another one, empirical distance uniform. This one is really strange because if you had asked me even 5 years ago if that one worked, I would have said, no, there is no way this can work. And somehow it works. The analysis is not simple, and it's quite surprising that it works at all. But the idea is, let's just do the obvious thing. We have a bunch of samples. We compute the empirical distribution over those samples. The thing I exactly said a few slides ago should not work because we don't see things well enough. Turns out, actually, just like computing the distance from that to uniform is good. And we're going to see a bit about that. Then there's another one called random binary hashing. I really like this one. That's why I put its fun in the notes. It has some big advantage. It requires very little memory. It's really fast. There's one big disadvantage, though. It doesn't achieve the optimal sample complexity. You can see that it achieves k instead of square root k. But if you're mostly concerned about the memory use, for example, or like some other applications, this is great. There's another one that's good for memory kind of thing, like the bipartite collisions. So if you work in a streaming setting or something like that, you might want to use this one. Same thing, it achieves the optimal sample complexity, but it also has some kind of inherent limitation on the parameter, like the distance parameter. Cannot be too small, essentially. And finally, there's another one that also seems kind of strange. And I like it a lot. Achieve the optimal sample complexity, but has a similar limitation. And that last one, I can tell you some of its advantages as well at the end. But my point is all of those, well, most of those achieve the optimal sample complexity. Some of them have extra things that can be useful. Some of them are also limitations. And we're going to go through some of that as well. Okay, is there any question? Otherwise, I'm going to jump into the first algorithm. So again, that's the roadmap. I'm not going to go into all the details, etc. I mean, I realize there's only something like 30 minutes or something left. I will not give you 70 pages of proofs. If you're interested, I can point you to the references. Some of them are here. I also wrote a survey on those, but this is just to give you some taste of the techniques. So there's one key insight, and that's a very important one. TV distance is L1 distance, right? It's half of the L1 distance. L2 distance by itself is not a very good way to look at distances between distributions, because it doesn't satisfy a lot of nice properties like post-processing, but it's a good proxy. Why is that? Well, you have Cauchy-Schwarz inequality that says that, if you are total variation distance at least epsilon, then you are at L2 distance at least something much smaller, but at least epsilon over square root k, like 2 epsilon over square root k. And this is just using Cauchy-Schwarz inequality. So that's good. What can we do with that though? Why is L2 simpler? That's the second part. The L2 square distance to uniformity has that very nice expression. It looks magical, but if you just square it and compute the thing and just, there's a square in the middle. What do we do with square? We just expand it. Just try it. Things cancel nicely because of the fact that the uniform distribution is very nice. And so what you get is the L2 distance squared to uniformity is exactly that strange thing, like the L2 norm of the distribution squared minus some constant, like 1 over k. And so if we want to estimate the L2 square distance, it suffices to estimate that other thing that doesn't depend on the uniform distribution. It's just the norm of the unknown distribution itself. So it would suffice to estimate that. Why? Because in one case, it's the uniform distribution, so that thing will be exactly 1 over k. And on the other case, by the previous slide, that thing should be at least 1 over k plus epsilon square over k, like something like that. So there's a small gap. So if you can estimate that quantity to sufficient accuracy, then we have a test. How do we do this? And that's why this quantity is really interesting. And that's where the name collision also pops up. Again, you can just check that. If you take 2 independent samples from the same distribution, discrete distribution, and you say, like, what is the probability that they're equal? This is exactly this quantity. This is exactly this L2 norm squared of the distribution. It's obvious once you've seen it, but I mean, this is kind of magical here. So the squared L2 norm is the collision probability. If I take 2 samples, what is the probability that they collide? So that's good. That gives me a natural idea. I take a bunch of samples and I check how many of them collide. And I divide by like 1 over n choose 2. Why would I do that? Just that gives me an unbiased estimator for that quantity, P2 square. And so, sorry about the sounds, by the way. I don't know how to mute them. So if I do that, then I'm actually in good shape. I actually get an unbiased estimator. If I can prove that it concentrates nicely around its expectation, then I am done. Is that clear to everybody? Why this is a natural idea to estimate like that collision probability? Okay. So again, I compute this thing. I check whether it's closer to 1 over k or 1 plus epsilon square over k. Depending on the result, I say uniform or far from uniform. So that seems good. The expectation is easy to compute, just linearity of expectation, I get the right thing. The issue is to compute the variance. So I want to argue that this thing will concentrate around its expectation. To do that, the obvious way would be, I have the expectation, I also compute the variance, I use Chebyshev's inequality. Things like do not go by too much, the probability to be far from your expectation by at least t is at most variance of the thing divided by t squared. If things go well, that will work. Now the issue here is computing the variance of these things is actually very tricky if I want to do it optimally. Getting like something is not too hard, getting the right dependence on epsilon will be much harder. And the reason is those summands, those indicators here is the S, the sample number S colliding with sample number T. They're not pairwise independent because, the probability that XS is equal to XT is not independent from the probability, like the random variable that says if XS collides with XR, for example. So I have to undo those dependencies, and that's kind of miserable, but that works. So yeah, here are the details. We're going to threshold that's Z1 statistic at like something between 1 over k and 1 plus 2 epsilon square over k to distinguish uniform apart from uniform. We want to use Chebyshev's inequality. This is not easy, but that works. And that gives a very simple algorithm. The second one is different. It says, don't worry about how many of them collide. Just look at the ones that appear exactly once. So I take, again, n samples, and I check the number of values I see exactly once. So again, that's kind of dual to the first one. You can compute the expectation of this thing. It has this it's closed form, right? But it's not easy to bound. Again, what we would like to say is in the uniform case that has some value, in the far from uniform case that has some other value, and there is a gap between the two. If there's a gap between those two expectations, and we can argue that Z2 concentrates on its expectation, then we can do the same, like, for example, using Chebyshev's inequality to say that with high probability, we can distinguish by thresholding in the middle. So just as a rule of thumb, if you use some approximation under the uniform distribution, this is roughly n minus n squared over k. And if it's far from uniform, you kind of hope that it's going to be roughly n minus, you make those approximations that are not very true in general, but you should expect that it's n minus n squared times the same quantity, that collision probability squared. And so if things were to go well, you would have that gap here because you get this. So that gives you that gap of like n squared epsilon squared over k. And maybe things work out. That's the gap between expectation. Then assuming the variance is small enough, you can use Chebyshev. All approximations, you have to argue that they're actually old because it's actually not true the way I've stated. And you will get the right test. And again, that you will get the right answer. So counting the number of elements that appear exactly once works as well. Now there is a catch. Does anybody see why? If you remember the table, I said but this only works if epsilon is not too small. Why is that? Well, that can't work if epsilon is too small. Sorry, that should be like too small, so less than 1 over k to the 1/4. And then the reason is, if you look at what that would imply, that the number of samples I take is much greater than the domain size, which is a very big problem if I count the number of elements I see exactly once, because if I start taking way too many samples, that will go to 0. I will see all elements like twice, 3 times, 4 times if I start taking many times the domain size in terms of samples. So that's an inherent limitation of that algorithm, just the quantity you're actually counting. If you take too many samples, that thing will just be 0 at some point. And there's not much you can do about that. So that's a small limitation, but it's good to keep that in mind. Now on to the third algorithm, chi-square. So again, if you've taken like some statistics class, there's the case like Pearson's chi-square test that appears everywhere. It's everywhere. What we want to argue is that it also works in that non-asymptotic regime. So really, like what we want to be able to say, like here's some value of n as a function of k and epsilon, square root k over epsilon square, such that if you take that many samples, then you can conclude. Well, typically in those statistics class, you'd have something saying like, as n goes to infinity, the statistic, the Pearson chi-square statistic converges in distribution or like into something that you can analyze. Here, you really want a finite sample guarantee. Can we get this? Here's what this test looks like. Ni is the number of times I see element I among my n samples. I compute this thing. That looks weird, but this is kind of a chi-squared type quantity. There's that extra step thing here so that it has the right expectation, making like some assumption I won't mention. Long story short, this gives the right expectation. Computing the variance is actually pretty simple, and that works. So, and that generalizes as well to a bunch of other things. So the chi-square statistic, given like a small modification for it to work out, gives the right answer as well, and it's pretty simple and takes linear time to compute. So that's our third algorithm. Again, if you have questions, otherwise I'm just gonna go through all 7 of them. So if at some point you just feel you need a break, let me know. So this one is nice. It still has some issue. And one of the issue that pretty much all of them have so far, at least the first one, like the collision base, the first one, and this one is like you're computing a square. So for most of the things, that's not an issue, but your statistic has a square in it, which means, so I don't know if you're like more of a mathematical band or not, but this is not going to be this is not going to be well behaved. This is not going to be like Lipschitz nicely in your samples. If you modify one sample arbitrarily, or if you're unlucky, that can change the value of the statistic by a lot. And most of the time, that's fine. But if you want to be robust to outliers, or if you want to have applications that require some kind of stability, if you have heard of differential privacy, that's one of the things where you want your statistic to be kind of nice and Lipschitz. Or if you want to have like a high probability guarantee using McDiarmid or things like that, this is going to be a problem. So essentially, those things work well, but they might fail if you want to get more from them than just the vanilla guarantee. That's just an aside, but yeah, if you see something that works by computing a square inside like this, there's a caveat. Oh, there's a question in the chat. Oh yeah, so there's a question about like, what about continuous case? So all of this is for discrete distributions over k elements. If you start doing continuous distributions, I can actually mention that right now. Total variation distance already is kind of tricky. You need to make some assumption on the unknown distribution. Otherwise, there are vacuous case, like trivial cases where like you can't get any guarantee. So you will need to make some assumption on the distribution. And like for those tests to apply, you will need to discretize your data in some way. Now, there are some black box ways to doing that. So if you deal with continuous distributions and you assume that the underlying density function is Lipschitz, for example, then like there's a black box way of saying you can use those algorithms I'm talking about that work for discrete data and just use them for continuous data using some kind of adaptive binning of the domain. And you will lose like a log factor in something in the distance parameter. So all this talk is about discrete distributions. I do know that continuous distributions exist, but there are ways to handle them. Yeah, hopefully that answers the question. But yeah, here K is the domain size, so you really assume the domain is finite.
I also have a question regarding this method. So like previously you mentioned about you counting the unique elements.
Yeah.
So here the Ni indicates like the number of times that we see the sample. So are we expecting this Ni to be 1 or something?
So yeah, that's a good question. The previous one was basically looking at ni and just counting the number of them that was exactly one. And all the things I've talked so far can be expressed as a function of those ni's. This one, we don't. It could be more. So it could be more than one. Most of them under the uniform distribution or something that is close to uniform will be either 0 or 1. But you could have some of them that are way more than 1 if your distribution is, puts way more probability mass on some elements than it should. And in this case, that will really help you, just because the square will grow big, and so you want like that statistic Z3 will actually be very large, and you will detect it easily. So yeah, ni could be anything between basically 0 and n, because you take n samples. So this one is the one I said is surprising, the plugin estimator, because collision-based, unique elements, chi-square. Why do we do that instead of doing the obvious natural thing, which is I've got data, I compute the empirical distribution, and okay, I'm not gonna just like plot it and see if it looks uniform, but I can compute the total variation distance of that thing to uniform, and maybe that works. I mean, why not? Take our samples, compute the empirical distribution. It's called plugin because you literally plug in your empirical distribution in the thing you're trying to compute and see what the answer is. So obviously that doesn't work, right? If I take the empirical distance, like if I take that empirical distance and I take n to be too small, well, most elements I won't see enough times or at all, and so I will basically have something that is at constant distance from uniform, even if my actual distribution was uniform, just because there's going to be a lot of gaps in my or a lot of things like that in my empirical estimator. So obviously that doesn't work. Turns out actually it does work. Like it does work, and that was very surprising to me. That was proven by Diakonikolas, Kane, Gouleakis like a few years back. And the idea is like, yes, it is going to be very, in both cases, either you're uniform or far from uniform, in both cases, that thing is going to be almost 1. Like the total variation distance is between 0 and 1, and in both cases, that's still going to be very close to 1. But that very close is not going to be the same. That little of 1, that like negligible little thing, actually is not negligible. That's exactly what's going to allow you to distinguish between the two. So you have to have an analysis that is very, very, very accurate of that thing to be able to pinpoint what is in that small negligible thing, because that's what's going to allow you to actually distinguish between the cases. So yeah, long story short, it does work. It was not obvious to me and to a lot of people it worked, but it requires a lot of care to be able to distinguish between the two cases. You need a lot more than Chebyshev's inequality for that one. So it is a very simple thing. That's the very natural thing to do. It's very fast. It has some other advantages. Once you have computed that empirical distribution, you can also do other things with it if you want. I don't find that intuitive at all. It is elegant. It generalizes in one sense. So what I said about like some others that computed a square, and so they're very brittle to outliers, this one doesn't compute squares, right? It just computes the empirical distance of that thing. Total variation distance is an L1 distance. So it actually is very robust to outliers. So again, if you have some applications in mind, like differential privacy or a lot of other things, like where you need some robustness to outliers or like things to be stable, this is great. This is the best you can get. It's also interestingly the first one we've seen that doesn't rely on that L2 norm as a proxy to test in total variation distance. So that one was complicated, but this one I really like. So because it's very obvious, it gives something obvious. So if you don't like big numbers, here the main issue is K, the domain size is really large. We want to achieve square root K, this, or like something like this. But there's one thing we know how to do. It's when K is equal to 2. If I give you a coin and I promise you it's either fair or biased, with like a bias alpha, we know how to distinguish between those two cases. You just flip the coin a bunch of times. Basically, you have a binomial distribution at that point after flipping, and you try to distinguish between the two. And we know that 1 over alpha square samples are enough to distinguish between fair and like biased, like 1/2 plus or minus alpha. So if we could just reduce our problem to this one, that would be nice. And there is a very simple way to reduce our problem to this one. Just we have a big domain, but we can just divide it into and see what happens. So divide, like partition the domain into randomly. You just take a random partition of the domain in 2. If it falls in that half, you say it's tails, otherwise it's heads. Now you have a binary, like you have a coin. So let's say we divide it in 2, and let's say equal parts for simplicity, 2 parts, k over 2 elements, k over 2 elements. If it was uniform, if the distribution was uniform, then you have a fair coin because the probability to fall on 1/2 is equal to 1/2. Great. If it was far from uniform, it's less clear that it's still far from uniform, but you can prove it is. The proof is actually not that hard, but you can prove that if you had total elevation distance at least epsilon from uniform, then like with constant probability over the choice of your random partition of the domain, etc., essentially your coin will be biased, and the bias will be no longer epsilon, much smaller, epsilon over square root k, up to some constant. And that's good enough to do something at least. Because we can use our fact, and in one case we have a fair coin, it was uniform, it's still uniform, but on k is equal to 2 elements. In the other case, it was far, and now it's like epsilon over square root k bias. So if you just use the previous thing, you get k over epsilon square sample complexity, which is not optimal. We don't get square root k, we get k. But I will argue this is very simple. You just hash the domain into halves. This is very fast. By the way, you can remove that. It doesn't need to be in equal halves. You can, like, if you do things like just in a random subset, that works. It's really fast. I find that kind of fun. It requires very little memory. All you need to is, I mean, if you want the fine print, what you need is like a 4-wise independent hash function, which takes very little space to do. And you just need to store after that very little. And it does generalize. What do I mean by that? I talked about privacy before. If you want to look at local privacy, a type of differential privacy, this is exactly the thing you want to do. This is optimal. If you want to look at communication constraints, I can only send a few bits and my data is distributed among many things. Well, now you just have to send 1 bit. So that's pretty good. It is not optimal. You get k instead of square root k. But again, for those 2 things I just mentioned, local privacy and communication constraints, like bandwidth constraints and distributed settings, this is actually optimal. So, and I mean, the analysis is interesting. That's like a nice exercise to do. So that has some nice properties. Yeah, I'm not gonna give too much details about that one. That one is, think of the collision-based tester we've seen before. Oh, I look at how many things collide and that gives me an estimator, etc. But now instead of looking at like all of the possible pairs and see if they collide, you just take 2 sets of samples and you see if the collisions are like something from the first half collides with something with the second half. It's not clear why a priori I want to do that, but I can define this that way. That gives you some flexibility. In particular, if you're in a streaming setting or memory constraint setting, you can use that to have a small set and a big set, and you got a trade-off between the 2. And all you need to do is remember like a small number of samples, and if the other ones come in as a stream, you just check if they collide with something you already have kept in memory. So that basically allows you to trade some memory usage with some sample complexity if you deal with like small memory devices and data that comes in a streaming fashion. But that is useful sometimes, essentially. And now you can also analyze that with Chebyshev. So when I say by Chebyshev, it's really compute the expectation, bound the variance, hope for the best. You hope that your statistic is concentrated around its expectation. And yeah, I'm gonna try to keep some time for questions or just, you know, things. If anybody wants me to go back to something. So the last one, the 7th and kind of weird algorithm. Take some of your samples. So you have n samples, take some of them, the first s of them. That gives you a multiset. You know, a multi-set of S samples. Multi-set because you might have the same value coming several times. See that as a set. So now you have a set of at most S values. Call that S. What is the expected mass that your unknown distribution put on that set? That has a form, like there's a formula for that, which is here. It's again, it's not necessarily nice, but you can compute it. If you make a few approximations, that's going to behave as roughly S times the collision probability, the L2 norm squared. So at this point, what you've done is that you've got a lot of samples, you've taken some subset of it, and you use that as, I don't know, a set of elements. You still have the other ones, so then use the other ones to estimate that thing, the probability that the unknown distribution puts overall on that set. It's very easy to do. You just check over the remaining n prime samples, whether they fall in that set or not. If they fall in it, you say 1. If they don't, you say 0. And then you compute the fraction of ones you have. And you can show that, like, you know, if it's uniform, that should, your estimate should be roughly S over K, and otherwise it should be, like, there's a small gap again, by roughly like S times epsilon square over K. So you can also see that as another strange way to reduce that to testing the bias of a coin. The first S samples give you like some partition of the domain in 2, which is no longer like a uniformly unchosen partition, etc. It's dictated by the unknown distribution itself. And then the second part is estimating that bias using the remaining samples. So I'm saying it's weird because we're doing something that is adaptive, right? I have to wait to see the first S samples in order to be able to process the remaining ones. There's no particular reason for which I would like to do that. It seems like I'm tying my hands in my back. But somehow that will work. So if you do the math, like a lot of wishful thinking, etc., you want to estimate that bias. If you look at that fact I had earlier, etc., what you will need is the second part of the samples, n minus S, to be at least this quantity, K over S epsilon square. If you optimize, well, the right thing to do would be to divide S is equal to n over 2, so first half of samples, second half of samples. That will give you the optimal sample complexity. So I would say it's kind of simple. It's fast to do. It's actually very fun to do. It generalizes. It's actually also something you might want to do if you have some constraints on the way you can process the samples, because all you need to do is keep a small set at first and then check which ones fall in there or not. It has some limitation. It's kind of tricky to analyze for sad reasons, but if I can drop some buzzwords, it's actually something that, like, for example, if you have like quantum computer, or at least you don't have a quantum computer, but like you say you can have a quantum algorithm, you can analyze this thing and get something that actually gives like a speed up for that particular problem in this case using this algorithm. So something kind of strange can happen, and that adaptivity actually helps, like the fact that you first look at some part of the samples and then like use that for the second part. So this is not totally unwarranted as a as an algorithm. So that's pretty much. Oh yeah, you can also check why you need it. Like you have the same restriction on epsilon; it cannot be too small. And if you can see why, it's basically the same reason. If you start having epsilon too small, that means that n is too large. But then when you start taking sample, like the first half of the samples, basically your multiset is going to be just very, very, very annoying. It's going to have every element multiple times, and then it's not a good estimate at all when we made that approximation here. Oops. When we try to relate this horrible quantity to something we know how to manage, there are a lot of approximations going in there. You can make them formal, but they break, all of them break if n is too large. So the analysis basically fails, and the algorithm actually fails. So again, this is, I hope I didn't put all of you to sleep, but this is the lay of the land. There are also some I haven't talked about because there are only 7 dwarfs in the story. But the point is, even for such a problem as simple as testing if some discrete data comes from the uniform distribution or something that's far from it, there are many ways to tackle the problem. Each of them has like some advantages, some disadvantages, some extra bonus features that you might you might not even see written down in the original papers, but people figure out afterwards. And applications beyond just the original thing people who develop those algorithms at. So that's pretty much all for the talk. I'm happy to take questions if there are any, or like go back to any point of the talk. But yeah, thank you.